Good. And so we got the expression for the refractive index to be sine of sigma plus, sigma plus what? Hello, what's the expression we got for the refractive index? Now, for a sine of hello, can you hear me? Hello. Oh, hello, can you hear me?
Please plus A.
So plus A.
Please, there's an M before the plus.
All over.
Sine A over 2.
Okay. This is the key. The expression for the refractive index at the minimum deviation. Okay. Adwa noted. So this is the expression for the minimum deviation. And we saw that the conditions that pertains at minimum deviation is that at minimum deviation, the ray passes through the triangular prism symmetrically. So ray passes through the triangular prism symmetrically, and the refracted ray is parallel to the base. Now, at minimum deviation, we realize that angle of incidence equals the angle of emergence. Okay. The angle of refraction 1 is equal to angle of refraction 2. Okay. And these were the considerations before we got this. Now, when we plot a graph of I against, it is a graph of deviation against I. Okay. When you plot a graph of deviation sigma against I, this is what you get for the graph. So I get a graph of deviation on the vertical axis and I on the horizontal axis. Okay. Please, it is I on the vertical axis against sigma on the horizontal axis, I on the sigma on the vertical, I on the horizontal, because you see the deviation sigma depends on I. Okay, so when I changes, we get the deviation within the glass prism. Sigma I does not depend on I. Sigma I, which is the angle of incidence, does not depend on the angle of deviation. It is the angle of incidence which would have to change to give you the angle of deviation. It isn't the angle of deviation which has to be changing to give you angle of incidence. But with graphs, we always plot the independent variable along the y-axis. So with graph works, the independent variable is always plotted on the y-axis. It's always plotted on the y-axis. And the dependent variable is always on the x-axis. It's always on the x-axis. So with glass prism, okay, with glass prism, if this is the normal, we vary the angle of incidence to get the angle of refraction, to get the angle of deviation, sigma. Okay, so when I changes, it gives us sigma. It is not sigma changing to give you I. Please, do you understand the explanation? Do you understand what I'm saying?
No, please.
So what I'm saying is that it is the angle of incidence that has to be changing to give us the angle of deviation within the prism. It is not the angle of deviation that changes. Anita, ask your question.
Miss Edia,
Yes,
please, you said that the independent variable will be on the y-axis.
No,
but on your graph, I is on the x-axis.
No, what I'm saying is that the independent variable, okay, the independent variable, okay, is always on the y-axis, okay. Then the dependent variable is on the, what I'm saying is that over here, sigma actually depends on, I think, hello, hold on a second. Hold on a second. Okay, so here it is the other way around rather. It's the other way around rather. Sigma depends on I. This sigma depends on I. Is that okay? So the dependent variable rather is a y, is a sigma. Is a dependent variable. Anita, thanks for the notification. The dependent variable is always plotted on the y-axis, and the independent variable, it means that over here sigma depends on I, okay, and I is on its own. Is that okay? I is the independent variable, so that is why we are plotting sigma against I. Are we okay? Please, are we okay? Implying that the angle of incidence must be changing to give you the angle of deviation. If you recall, I said that a changing angle of incidence gives you angle of deviation. So when the angle of incidence is increasing gradually, then we realize that the angle of deviation will be decreasing. Okay, so when you plot this against this, you have this curve. When you plot deviation against angle of incidence, you have this curve. Now, when you look at it, let's assume that I changes in this manner. Okay. I cannot be zero, because when I is zero, we wouldn't have any deviation within the prism. When the angle of incidence is along the angle of the normal, no deviation would occur. So I cannot be equal to zero. That is why the curve doesn't touch the vertical axis. That's why we don't have this. Because when I is zero, there wouldn't be any deviation. So we start with a certain larger value of I. Okay. Now, assuming I is this, we'll have the deviation to be this. When I increases to this, the deviation will be here. If I is this, the deviation will be here. Please, what do you think is happening to the angle of deviation as I increases? Yes, as I increases, what is happening to the deviation?
It is decreasing.
It is decreasing. Is that okay? So it follows the norm. Then we get to a point where I gives us the least deviation, the minimum deviation. At that point, we have sigma m, the minimum deviation. Now, at this minimum deviation, we have that special condition that I is equal to E. So this minimum deviation goes with this condition. I is equal to E, R1 is equal to R2. Now, if I continues to increase, let me bring it here. I is this, that's it. I is this, we have deviation here. I is this, what is happening to the deviation as I continues to increase? As
It
I
is
continue,
increasing.
it is increasing. So it obeys the theory we learned that as we increase the angle of incidence gradually, the deviation, the angle of deviation would also be decreasing. But it will do so to a certain minimum value. And from there, as we increase I, sigma begins to increase. So the graph is in line with the theory. Please, are we okay? Are we okay?
Yes, please.
So that is the explanation for the graph of angle of deviation against the angle of incidence. It just explains the theory. If you have any question, quickly ask. If you don't have any question, this is the ending of refraction in triangular prism. Then the next thing we have to be doing is to give you questions to try. Okay, then we answer and then move forward. Today we are going to continue with total internal reflection. Total internal reflection. If there is time, then we look at refraction in lenses. So total internal reflection. Please, what is total internal reflection? Yes, if any of you has an idea about total internal reflection, quickly share it with me. Mary, do you have any idea? Hey, Mary is quiet. Nana, do I? Any idea?
Please, refraction.
Total internal reflection.
Reflection.
Total internal reflection. Any idea or no idea? Adwa, any idea? Okay. Then let me take it upon myself. Now, whenever you have light coming from a dense medium or a denser medium into a less dense medium, which we also call as a rare medium. So over here we have mu of the dense medium, refractive index of the dense medium. Then we have the refractive index of the rare medium. This line represents the normal. So whenever you have light traveling from a denser medium into a less dense medium, so this is the incident ray. Irene, What is the name given to the angle between the normal and the incidence ray? What's the name given to it? Irene, are you there?
Please, can you come again?
What is the name given to the angle between the normal and the incidence ray?
Angle of incidence.
That's the angle of incidence, I. Now, whenever light interacts with another medium whose density is greater than the first medium, two things would happen. Part of the light will be reflected. Part of it will be refracted. The refracted ray, please, since it is traveling from denser medium into a less dense medium, will it refract away from the normal or towards the normal? Adelaide, will the deviation be towards the normal or away from the normal? Adelaide.
Away from the normal.
Thank you. So away.
Away from the normal.
Yes, away from the normal. Okay. And so this is the angle of refraction R. This is the angle of reflection R, which is actually also equal to I, the angle of incidence. Now, as we increase the angle of incidence gradually, angle of incidence. When you draw another sketch, angle of incidence, this time we are increasing it. I. This one, the refracted ray, this is the reflected ray. You realize that the refracted ray bends towards the normal the more. Now you realize that this refracted ray, as you increase the angle of incidence, it will be bending towards the normal. Its intensity will be brighter. Whereas the reflected ray is weaker in terms of intensity. What are we doing? We are increasing the angle of incidence gradually. So another increment in angle of incidence. Then you realize that the refracted ray is so close to the boundary. There's a boundary between the two media. This is still brighter, whereas this is weak. A certain angle, we are increasing it. There will be a certain angle within the denser medium where the refracted ray, oh no, it's then I think it's
Yes,
please. Hello, Nadia, do you all have that difficulty in seeing what is on the board?
Yes, please.
Hey, let me take a shot and send to the group. But I hope you can hear me.
No, please.
Yes, please.
Yes, please.
So I've sent a shot into the group, okay?
Thank you.
So what we are doing is that we are increasing the angle of incidence gradually. A certain angle of incidence in the denser medium would give us a point where the angle of refraction will lie on the boundary direct, will be on the boundary. Here, if the refracted ray lies on the boundary, then what will be the angle of refraction? Yes, what do you think will be the angle of refraction if the refracted ray is on the boundary? Yes? Anybody to?
90 degrees.
So you realize that the angle of refraction would be 90. Now, the angle of incidence in the denser medium, that gives you an angle of refraction of 90 degrees in the less dense or rare medium, is what we call as the critical angle, represented by the letter C. So we define the critical angle as the angle of incidence in the denser medium that gives an angle of refraction of 90 degrees in the less dense medium or the rare medium. Are we okay?
No, please can you repeat?
The critical angle C is the angle of incidence in the denser medium that produces an angle of refraction of 90 degrees in the less dense medium. All right. So that angle of, as you increase the angle of incidence in the denser medium gradually, bit by bit, a certain angle of incidence in the denser medium would give you an angle of refraction of 90 degrees in the less dense medium or in the rare medium. And this angle of incidence in the denser medium, which gives you an angle of refraction of 90, is what we call as the critical angle, C. Now, at the attainment of the critical angle, okay, if you increase, or if you go beyond that angle of incidence, which gives an angle of refraction of 90, a little, whenever, if it's 20, the moment you produce an angle of incidence of 21, 22, this is what you observe. You realize that this refracted ray, okay, would reflect 100% within the denser medium. And when you have that condition, the reflected ray, which was before then weak, will then be brighter. All refracted ray now becomes reflected ray. And this condition is what we call as total internal reflection. I'll take it again. Okay. So let me clean this, go over for the last time. So here we have a denser medium. Denser medium, we have rare medium or less dense medium. The refractive index of the denser medium is mu subscript D. The refractive index of the rare medium, mu subscript R. Light must travel from a denser medium into a less dense medium. When it's the other way around, it won't work. So all that we are doing is that we are progressively increasing the angle of incidence within the denser medium. Now, but whenever light travels from a dense medium into a less dense medium, or whenever light travels from one medium into another, two things. Part of the incident light will be reflected. So we'll have reflected ray. Part of it will be refracted ray. Now the observation is that you realize that the refracted ray will be brighter or stronger in intensity. Let me use stronger, even though brighter will also work. And then the reflected ray is weak in brightness. Now we are increasing the angle of incidence progressively. Okay, so if you increase it, you still have refracted ray, reflected ray, but you realize that the refracted ray will still be brighter or stronger, whilst the reflected is still weaker in brightness. Now, a certain angle of incidence within the denser medium would produce a situation where the refracted ray lies just on the boundary between the dense medium and then the less dense medium. And over here, that angle of incidence in the denser medium would give you an angle of refraction of 90. Still, refracted ray brighter, reflected ray weaker. But that angle of incidence in the denser medium, that produces an angle of refraction of 90 degrees in the rare medium or less dense medium is known as the critical angle. Critical angle. After the attainment of the critical angle, any increase in the denser medium, now all the light, incident light, will be reflected, and there wouldn't be any refracted ray. We'll have a complete reflection. And here, the reflected ray, which before then was weak, would be stronger in intensity. So we have a situation of 100% reflection of the incident light. And this we call as total internal reflection. Please give me a second. Let me put the laptop on charge, okay? Total internal reflection. So, Deborah, ask your question.
Mr. Dua, please, are you saying that when the refracted ray is exactly at the boundary and the 90 degrees angle is formed, the reflected ray becomes stronger?
You see, no, what I'm saying is that when the angle of refraction is 90, we have the refracted ray on the boundary, lying on the boundary between the denser medium and the less dense medium. At this point, there is refracted ray and it is still stronger whereas the reflected ray is weaker. So at the attainment of the critical angle, the refracted ray, which is just on the boundary, is still stronger. And the reflected ray is weaker in intensity. Now, after the attainment of this angle, we are calling as the critical angle C. Any increase in the angle of incidence causes this whole light to reflect. Here, we wouldn't have anything refracted ray, but we have complete and absolute reflection of the incident light. Are you okay? Deborah, are you okay?
Yes, please. So, Mr. Dua, please, you are saying when the refracted ray is on the boundary,
Yes.
and if there's any little increase of the incident ray, it will reflect completely.
Total internal reflection. Where this angle of incidence is equal to the angle of reflection R or cell I. So the requirement for the attainment of total internal reflection is that there must be a critical, you have to determine the critical angle of the denser medium. Once you obtain the critical angle, you can now adjust the angle of incidence to have absolute or total internal reflection. Are we okay?
Yes,
Mr.
please.
Dua,
Hello, Edubia.
so please, total internal reflection is when the angle of after the angle of incidence causes an angle of
Okay, I'll give you the explanation of
reflection greater
total.
than.
Edubia, I'll give you the explanation of total internal reflection. Okay.
Yes, please. And said you mentioned total absolute reflection.
Oh, it's the same thing. Absolute reflection or total internal reflection, the same way.
Okay. All right.
Eliana.
So please, that means that the new reflected race angle is equal to the incidence angle.